we can now look at the sources of acceleration. So acceleration in projectile motion can come from other sources as well. So questions aren't just going to be like what we had before, where it's like a toy bird or like a projectile or something is launched, because in this case the force is acting as gravity. They can also simulate this type of scenario or emulate this type of scenario in, let's say, like perpendicular electric fields, or like uniform electric fields, like between two perpendicular charged plates, where like you can say ignore gravity and an electron is going through the plate. In this case, there will be a constant force formed by the electric field, right? So that's why you can see a visualization over here. So yeah, the acceleration that comes in these examples is not necessarily from gravity. So we could have E is equal to V over D. So then F is equal to QE and A is equal to F over M. So there are different scenarios where we could get acceleration from other sources as well. Again, here I would really recommend familiarizing yourself with the data sheet, so you know all the formulas. So E is equal to V over D. So they could give you like voltage and distance and ask you to find like the acceleration that an electron will experience, for example, and that might stump a lot of people. Well, familiarizing with yourself with the data sheet will allow you to realize that, oh wait, voltage and distance, I instantly have E, and so I can find F is equal to QE, given that they said it's an electron, so I have charge as well, and so I can find mass as well. I can find acceleration as well, sorry, because I have mass in my formula sheet, so A is equal to F over M. So yeah, just familiarizing yourself with all the info and knowing that acceleration can come from other sources as well. Now we can go through circular motion. The inquiry question in this is, why do objects move in circles? So, uniform circular motion is the motion of an object traveling in a circle at a constant speed. So in this case, the speed is constant. Velocity vectors are changing by therefore by the equation A equals V squared over R, acceleration is also changing. So that's something that's very important, and the fact that acceleration is changing, it might not even be touched on in this module, but it will definitely be touched on in things like module 6 and module 8 as well. So yeah, but these are kind of the constant features of uniform circular motion. The fact that the speed is always constant, the velocity vectors are changing because, well, the direction is changing, and so hence velocity is also changing, and the fact that acceleration is also changing due to the direction changing. So what does this mean then? F is equal to ma, acceleration is not equal to 0, force is not equal to 0, because again, distance is changing. So there's going to be a net force, and that net force is what we call centripetal force. So the net force inwards is what we're going to be calling centripetal force. That will be denoted by F is equal to mv squared over r, right? Because it's F is equal to ma. And so by the formula, or by the equation, A is equal to V squared over R, we can get F is equal to mv squared over R. So the definition then, centripetal force is the force that directs objects towards the center of a circular path. That's what you would say the definition would be. So, all right, so as I mentioned before then, centripetal force is a resultant force, and centripetal force always points towards the center of a circular path. So always towards the center. So because it will act in kind of the same direction as acceleration, always act towards the center of a circular path. And this will kind of come into play when we touch up on module 6, where you'll observe the motion of a charged particle in a magnetic field. But yeah, centripetal force always acts towards the center of a circular path, and centripetal force is also always a net force. So you don't end up drawing centripetal force in a force body diagram, because we don't end up drawing the net force. We only end up drawing like direct forces that act on it. So centripetal force is a type of net force or resultant force, and so we don't draw it in the force body diagrams. So doing this question now, find the centripetal force experienced by the mass with tension of 10 newtons and an angle at 30 degrees. Well, centripetal force is a resultant force and points to the center of a circular path. So what we do is we'd follow the steps, we'll draw the force body diagram, and then we'll resolve the vectors, right? Because it would be the net force. So if tension is acting like this, and I'm assuming the ball isn't just falling down, then that means that the vertical forces are balanced, which means that the only other vertical force that can counteract gravity can be the vertical component of tension. So the force so if I imagine a triangle like this, right? A triangle like that. This vertical component, hopefully you can see my cursor. Hopefully if you can see my cursor, the vertical component of tension will be the force that counteracts the force of gravity. And so now the object won't be moving in the vertical direction. But there's a resultant force that points towards the center of the circular path. And this will be the unresolved horizontal component of tension. So in this case, the horizontal component of tension will act as the centripetal force. How would we solve the horizontal component of tension then? Well, we can do 10 cos 30, because cos 30, so 10 cos 60, sorry, because cos 60 will be this horizontal component, or 10 sine 30, same thing. So 10 cos 60 or 10 sine 30, depending on where you draw your triangle, essentially. If I draw my triangle like this, right? If I draw my triangle like this, if you can see my cursor, then the answer will be 10 sine 30 to find this component. If I draw my triangle like this though, again, hopefully you can see my cursor, the component will be 10 cos 60, and that will be equal to 5 newtons. All right, so what is then the centripetal force on a bank track? So again, it would be to draw diagrams. Force is the vector sum of the normal and weight force, right? Centripetal force will be the vector sum of the normal and weight force. And so to calculate, you should find the horizontal and vertical components of both forces and then add them. So I think this one will be a similar scenario to our tension question, where the normal force, the vertical component, will balance out with gravity, and then we have left the horizontal component of normal force that will act as the centripetal force then. So yeah. Now we can move on to torque. So torque is the turning moment of a force. So we have torque is equal to RF. The next tip is don't memorize whether to use sine theta or cos theta. So a lot of times you might see in textbooks or something, you might see RF sine theta. So that is kind of misleading because it's assuming that the angle is directed in one way. What the actual formula is, and I'm pretty sure this is what's on your formula sheet as well, what it's actually looking for is RF, so R perpendicular F. So when the force acts in the perpendicular direction, that is what they're looking for. So keep that in mind. So don't memorize whether to use sine theta or cos theta because it changes case by case. And a lot of questions are designed so you can't use the formula as itself. So you can't use RF sine theta. You'll have to look at whichever way the force is perpendicular. So because I mentioned that now, we can say now, torque is achieved by applying a force perpendicular to the object. All right, so let's now look at motion in gravitational fields. So how does the force of gravity determine the motion of planets and satellites? So this is like the more content part of module 5. So definition then, orbital motion is a uniform circular motion of an object whereby the centripetal force is provided by gravity. So we can use this to find orbital velocity as well, which is the minimum velocity required for an object to orbit a planetary body or an object to orbit a planet, for example. So within these two equations, we have U is equal to negative gmm over r, that is gravitational potential energy, and F is equal to gmm over r squared. So in this case, r is the distance from the center of the mass, and r is an altitude is equal to, so yeah, r in this case is the distance from the center of the mass, whereas altitude is altitude, right? R is equal to the radius of the planet plus the altitude. So in altitude questions, you need to say, this is where things get confusing as well, because it can say a satellite is at an altitude of something. You need to be sure if they've accounted for the radius of the planet as well, because that's a case where a lot of people end up making calculator errors as well. Their method could be right, but they forget to add the radius of the planet as well. And that could be a place where a lot of people lose marks as well. But yeah, we can now move on to gravitational potential energy. So all these definitions, they could be tested in like 1 to 2 markers. So yeah, just make sure you know the content, right? So gravitational potential energy is the energy possessed by an object when it is raised in a gravitational field. And what we need to know about this is GPE always holds a negative value. That is because GPE originates or equals 0 or originates at some point infinitely far away. And so the further away we get from it, the more like we're negative, right? So we're in the negative values. And so because we're talking about gravitational potential energy being zero at a point infinitely far away from the point that we're measuring from, we will always be in like GPE will always hold a negative value. That doesn't mean that the change in GPE is different, because the change in GPE can be positive, but GPE standalone can hold is always a negative value. So we have now two formulas, right, that we should know: escape velocity and orbital velocity. I'd recommend in your questions deriving these formulas, because I don't think it's in your data sheet. So if you have a formula in your data sheet, you don't need to derive it. If it's not in your formula sheet, then you would have to derive it, because it's not considered like known, like pre-known content. So with escape velocity, if we're gonna derive the equation, we can let energy initial equal energy final, right? Because there's conservation of energy. So what we'll do is we'll break it down. So we have initial gravitational potential and initial kinetic, so U plus K, and initial and final gravitational potential and final kinetic, right? Let's think about what escape velocity means. Escape velocity is the minimum velocity required for an object to escape the gravitational field of the thing that it's trapped in, right? The minimum velocity required. So at that minimum velocity, because it's minimum velocity, as it like reaches the very end of, as it's like finally escaped, right? Because it's minimum velocity, the moment it escapes the gravitational field, it will basically run out of speed, right? Because it's the minimum velocity required, so that it will use up all of its energy to basically leave the field. And because of that, we can say kinetic energy is zero, because after it leaves the field, it will stop moving, because it's a minimum energy required. So half mv squared is equal to zero. Same way, we can also say GPE is also equal to zero, because when we've escaped the gravitational potential field, that basically means we have reached that point that is infinitely far away, that point where GPE equals zero. And so we can say now our final E is equal to zero. So now we have energy initial. So we have half mv squared is equal to minus gmm over r. So we have half mv squared is equal to gmm over r. So solving that formula now, we can do v squared is equal to 2gm over r, and we will get our escape velocity value as v equals root 2gm over r. So that is our value for escape velocity. And we can also solve orbital velocity. So what will we do when we're solving orbital velocity? Well, if you think about the setup for orbital velocity, we're just like in orbital velocity, it's not always uniform circular motion, like it's elliptical, like the Earth will orbit the sun in an elliptical orbit. But for the sake of the equation, we're going to consider it as uniform circular motion. So if that if that object is undergoing uniform circular motion over the planetary body, then that would mean that there will be a centripetal force, right? Centripetal force in this case would act perpendicular, right? And if it's acting perpendicularly, it will basically be acting downwards, right? Downwards towards the center of the Earth. The only other force that acts downwards towards the center of the Earth that we currently know of is gravity. So in this, to solve orbital velocity, what we do is we let the centripetal force equal to gravitational force, as you can see over here. So we have mv squared over r is equal to gmm over r squared. So we have v squared is equal to gm over r, and then we have v is equal to root gm over r, sorry. So escape velocity, v is equal to root 2 gm over r, and v is equal to root gm over r. This is another reason why I recommend that you guys aim to derive the formulas, because you can get confused. So because these two formulas are pretty similar, you can end up getting confused. But if you derive them, then you generally have an understanding of where the formulas come from, and you're also able to explain that understanding and show that understanding in your answers as well. So yeah, basically the total energy is equal to U plus K. So total energy in this sense can be calculated by U plus K, which will be equal to negative GMM over 2R. Negative GMM over 2R. The change in energy between orbits is equal to final energy minus initial energy. increasing orbit equals positive work, which equals positive change. Decreasing orbit equals negative work, which equals negative change. So for this question, for the question u plus k, we will use our value for we'll use our known value for velocity, which will be orbital velocity in this case. So yeah.